Hey guys, today in this video we are going to see the concepts in the water treatment and its methods. Let's start with the first question. Which of the following types of settling phenomenon can be analyzed by the classic sedimentation laws of Newton and Stokes? Now we have four types of settling, that is settling phenomenon, which is nothing but discrete settling, flocculent settling, hindered settling and compression settling. So which type of settling phenomenon will be applicable to Newton and Stokes sedimentation laws? So the discrete settling type of phenomenon, that is discrete settling phenomenon, will be applicable to Newton and Stokes. Now we shall see one by one what is the type of settling and what are the main points to be pondered. So first one is discrete settling. It means the particles settle as individual entities. So here you can see the particle will be settling as a individual entities. It won't clog, it won't coalesce, or it will not form a flocculant. So that is called as discrete settling, that is particles settle as individual entities. So that means the particles do not change in shape or size. So the particle which is inert, which will be settling as it is. So the particle do not change in size and shape. And this discrete settling will occur when the suspension of low solid concentration is there in the water. So low solid concentration should be there so that discrete settling may happen. So example, we have grit chamber. Now next type is the flocculent settling. Here the particles will coalesce or flocculate during settling. So that means one particle will be coagulating with another particle so that the mass will be increasing and the settling time will be very faster, because the weight of that particle will be more, that is increase in mass of that particle due to flocculation. So settling will be happening in a short duration of time when compared to the first type of discrete settling. Now here we have this condition: the suspension should be dilute and the concentration should be less than 1000 milligram per liter. Next point is the contact opportunities, surface flow rate. These are the factors that will affect the flocculent settling. One is the contact opportunities, how far a particle can contact another particle so that it can create floc. So that is called as contact opportunities. And surface flow rate, so surface flow rate directly affects the settling velocity. We shall see more about this surface flow rate and settling velocity in the upcoming questions. And the depth of the sedimentation tank, concentration. So we have already seen the concentration value should be less than 1000 milligram per liter, and the range of particle size and the velocity gradient. And we shall see about this velocity gradient or temporal mean velocity gradient in the upcoming question. Next point, example like removal of organic suspended solids, bioflux in upper portion of secondary settling tank. So these are some of the examples for flocculent settling. So and third type is the hindered or zone settling. So there will be a interparticle forces, that is force between the particles, and the intermediate concentration. Concentration will be intermediate of the first type and second type, like that, and it will maintain the relative positions. So relative positions between the particles will be maintained during hindered or zone settling. The whole mass settles as one unit or zone. This is unlike the flocculent settling. Flocculent means the floc will settle from top to bottom, but here whole mass will be created and that mass will be settling as one unit to the bottom. So that is called as hindered or zone settling, and it will be used for settling column analysis. So this is the third type, hindered or zone settling. And the fourth type is, so before moving to fourth type, let's see the thickening of sludge. So thickening of sludge happens due to hindered or zone settling. This thickening of sludge is already dealt in the sewage treatment video. Please watch that video so that you may know about the thickening of sludge. And fourth type is the compression settling. Now we shall see about this. This settling will happen when there is a very high concentration of suspended solids or bioflux, like that, and the physical contact between the particles will be more. The structure with lower layers support the weight of upper layers. So that means this is the lower layer. This lower layer will support the upper layers because of compression. So compression will squeeze out the water, and supernatant liquid will be formed due to compression settling. This supernatant liquid will be formed when there is a sewage treatment, like that, not in drinking water requirements. So these are the four types of settling phenomena we have seen now. Now let's move on to the second question. Fine screens are in the form of wire mesh with opening. So what is the size of opening in the fine screens? So screening is done as a pre-treatment. So we shall see what are the pre-treatment and what are the devices we use during pre-treatment of water. And here the question is fine screens. So the size of opening in a fine screen shall be less than 10 mm. And we have also these coarse screens. So in the pre-treatment method, we have some of the treatment devices, treatment methods. Let's see one by one. So first is the screening. The screen will be placed at an inclination of 45 degree to 60 degree, or we can say 3 to 6 vertical to 1 horizontal. So this much inclination to be given to that screen so that we can reduce the flow velocity. And next is the micro strainer. This micro strainer will be used for stored water. So stored water means we can use for lake supply and large storage reservoir. So in case of these things, we can use micro strainer. Micro strainer is nothing but there is a fabric like material. So in that all the coarse materials will be retained. So that is the micro strainer. And next is the raw water storage. This is called as the first line of defense in case of pre-treatment. Whenever a water is stored for a long time, there may be a fungal growth. So that is why the raw water storage should be pre-treated. And that is called as the first line of defense. And we have the pre-chlorination. The doses may be about 2 to 5 milligram per liter. And due to pre-chlorination, there may be precipitates of iron and manganese. So treat clear water with high ammonia content. So this pre-chlorination will treat the clear water. If the water is very clear but with high ammonia content, then we have to move for pre-chlorination. If the water is turbid, then we can move up to 2 to 5 milligram per liter or less than that. But if the water is clear but with high ammonia content, then we have to move for pre-chlorination. Next is the aeration. Aeration also removes iron and manganese but increases the acidity of water. So more amount of aeration should be avoided because it increases the acidity of water. And next is the algae control. So algae can be removed by using copper sulfate up to around a dosage of 2 milligram per liter, or we can even use the chlorine at a dosage of 3 to 5 milligram per liter. And last is the pre-settlement basins. So this will be used when suspended solids concentration is greater than 1000 milligram per liter by dry weight, and the detention time will be 1 to 3 hours. So these 7 are the devices will be used for pre-treatment of water. Before the sedimentation flocculation, we have to pre-treat the water. So by using pre-treatment, we can get rid of the coarser particles by using screening, microstrainer, raw water storage, and in case the water with high ammonia content, then we can go for pre-chlorination. And aeration, algae control will be removed by algae will be removed by copper sulfate, and last is the pre-settlement basins. So we know about the pre-treatment techniques. Now let's move on to the next one. Find the settling velocity of a discrete particle in water under the conditions. So when the Reynolds number is less than 0.5. They have given some of the data regarding the particle size, that is particle diameter is 0.005 centimeter and the specific gravity is given as 2.65. The temperature of water is maintained at 20 degrees Celsius. The kinematic viscosity of water at 20 degrees Celsius is 0.0101 centimeter square per second. So they have mentioned clearly that the particle is discrete and the Reynolds number is less than 0.5. So if the particle is discrete, then that means discrete settling will be happening. So we can use Newton's sedimentation law. So like that, Newton's or Stokes sedimentation laws accordingly to the given data. So we shall see the formulas regarding that. Now here the correct option is option A, 0.224 centimeter per second is the settling velocity of this discrete particle. Now we have some 4 formulas regarding the discrete settling. One is the Stokes equation, that is given for laminar conditions, and another one is also the same laminar condition but when the temperature is given. And next is the Hazen's equation when the condition is transition, that is transition flow condition, and Newton's equation will be used when the flow condition is turbulent. Now let's see one by one. So first equation, that is Stokes law, will be applicable to laminar flow conditions when the diameter of particle is less than 0.1 mm. So here we have the diameter of particle 0.005 centimeter, which is much less than 0.1 mm. So that means we can use this formula for this kind of problem. So here we have z nothing but 9.81 meter per second square, and z minus 1, capital G is nothing but the specific gravity 2.65, and d square, d is the particle dia, that is here they have mentioned in centimeter, but we have to change it to meter or something accordingly so that the homogeneity will be maintained. And gamma is the kinematic viscosity. They have also given the kinematic viscosity of water is 0.0101 centimeters square per second. So substitute accordingly with the proper unit so that we can get the answer for Vs. That is, here we got 0.224 centimeter per second. So this Stokes equation will be applicable only for laminar flow condition and when the particle size is less than 0.1 mm. Now let's see the next equation. Here this is also applicable to laminar flow conditions and diameter when less than 0.1 mm, but the temperature equation will be followed. Vs is equal to 418 into z minus 1 d square 3t plus 70 by 100. Here they have mentioned the temperature as 20 degrees Celsius, and we know all other terms, d we know, and we know the specific gravity also. So we can use either of these relations, but make sure that the answer will be more than of those formulas. If the answer coming out here, for example say 0.204 and here 0.224, then we have to adapt only the higher of the values. So we have to use both the formulas and select which is the highest value, which is the higher value of these both, of either of these. So we have seen the laminar flow condition. Now let's move on to the Hazen's equation. This will be applicable for transition flow conditions or when the diameter of particle is between 0.1 mm to 1 mm. So here this formula is purely dependent on the temperature only. So without temperature we cannot find the Vs, that is settling velocity. So here Hazen's equation goes like this: 418 into z minus 1 d into 3t plus 70 by 100. So this formula will be applicable when the particle size is between 0.1 mm to 1 mm and the flow is under transition condition. Now let's see the Newton's equation. Vs is equal to 1.8 root of zd into z minus 1, and this will be applicable to turbulent flow condition or when the particle size greater than 1 mm. So we have seen the 4 important formulas regarding settling velocity. Now let's move on to the next question. Two primary settling basins are 26 meter in diameter with a 2.1 meter side water depth. Water flow is given as 26,000 meter cube per day. We have to select which options are correct. Surface area of each tank is 623 meter square. Is this correct? And the overflow rate is given, detention time, and wear loading rate. So which of these options are correct? It is a multiple select type question. We have to select which are all the options are correct. So this is a circular settling basin, so that is why they have given diameter of the basin. So 26 meter is the diameter of the circular basin, and here the option A, B, C, first 3 options are correct and the wear loading rate is wrong. Now let's see the formulas how to determine the values. So for circular tank, the detention time is given by d square into 0.011 d plus 0.785 h by q. We have d, that is the diameter of the circular tank as 26 meter, and h is the side water depth, that is given as 2.1 meter, and q is the flow rate. Here they have mentioned as 2 primary settling basins. So for 2 primary settling basins they have given the flow rate, and we have to consider for the one tank. For one tank, what is the flow rate? Divided by 2, 13,000 meter cube per day. So q is 13,000. So upon substituting these things, we will get the detention time as 2.414 hours. And similarly we can find the surface area. Surface area is given by volume by depth. So volume by depth gives the surface area of the circular tank, and overflow rate is given as Q by A. So upon substituting the data, we can get the answer for surface area of each tank and overflow rate. And for wear loading rate, we have to find the length of wear. Length of wear is nothing but the perimeter, that is pi into d. So in this case we have pi into d because it is a circular tank, and wear loading rate is given as discharge by length. So these are the important formulas when it comes to circular tank. Now let's see about the formulas for rectangular tank. So for rectangular tank, detention time is LBH by Q, that is nothing but volume by discharge, or we can even use this relation, length of the tank divided by V suffix H. V suffix H is nothing but the horizontal flow velocity. So here you can see the water inflow here and moves like this. So this velocity is termed as VH, that is horizontal flow velocity, that is flow rate, that is given by Q by BH. We have to be careful about these formulas in case of rectangular tank. The flow rate is given by VH is equal to Q by B into H. B into H because this is H and this is B. Flow is coming like this. So B into H is the cross-sectional area when we have to find the flow rate, and this is the length. This is the length of the rectangular tank, and when we are considering the overflow rate or surface loading rate, that is V naught, that is equal to Q by L into B. L into B is the surface area. So when we have to find the surface loading rate, then we have to consider the surface area, that is L into B. We should be careful when we are using the area of rectangular tank when we are finding the rate, that is the velocity. So coming back to this, detention time is equal to L by V suffix H, and the settling time is nothing but H by Vs. So Vs is the settling velocity and H is the height of tank. So height of tank is, so settling will be happening from top to bottom, so that is why we are considering the height of the tank. Detention time will be happening over the length of the tank, because from here inflow happens and here outflow happens. So that is why we are considering the length of the tank. So length by VH, settling time is equal to H by Vs. And here length of wear is L and wear loading rate is simply discharge by length. So these are the important formulas for a settling tank in case of a rectangular tank, and we have already seen the formulas for circular tank. Now we shall move on to the next. Find the efficiency of sedimentation tank by using the given data. So they have given a table regarding size, quantity and settling velocity, and they have also given the overflow rate, that is V naught, that is 0.35 millimeter per second, and total suspended solid concentration as 1000 gram. So total suspended solids load is given as 1000 gram, overflow rate, and we have given the table and corresponding quantity and size. We have to find the overall efficiency of this sedimentation tank. So how to find that? Let's see. Here the option C is correct, 87.85%. So concept is, if a particle having settling velocity greater than or equal to overflow rate or surface loading rate, then that particle will be removed 100%. So here, which is the particle having settling velocity more than overflow rate? Here you can see overflow rate is 0.35. First particle, that is having size 0.1 mm, having settling velocity 0.2, which is less than overflow rate. So that means 100% of this particle will not be removed. So how much percent of this particle may be removed? That is nothing but 0.2 by 0.35. And similar is the case for second particle, here 0.25, which is less than overflow rate. So then how much percentage of particle will be removed? 0.25 by 0.35. And similar is the case for third particle, that is having 0.3 mm per second as settling velocity. So how much percentage will be removed? 0.3 by 0.35. And fourth particle having 0.35 as the settling velocity. That means this particle, this fourth size of particle will be wholly removed. And similar is the case for 0.4 and 0.5. That is fourth, that is fifth and sixth particle. So that means the particle having more than 0.35 millimeter per second as settling velocity, those particles will be 100% removed. So that means 5, 30 and 20, these percentage will be 100% removed. So 35 plus 20, so that is 55% of this particle will be wholly removed. And among these, the remaining quantity of particles, how much particles will be removed, that we have to calculate. So when we calculate that, we will get the answer as 87.85. So that is the concept. Simply, if a particle having settling velocity greater than or equal to overflow rate, then that particle will be removed 100%. Now let's see more about the percent removal thing. So overall percent removal will be given by this equation, 1 minus xx plus integration 0 to x suffix s with vs dash vs dx. So let's see what is the terms mean. X is nothing but the fraction of particles having settling velocity less than the stated velocity. X suffix s is the fraction of particles having velocity less than overflow rate. So understood. We have already seen what is overflow rate and what is settling velocity. So accordingly, what is that fraction? So when we substitute and integrate those values, we will get the overall percent removal. So that is what we have done by using this table. If the table is not given but given in some other terms, some other formation like graphical thing, then we have to use this common relation, 1 minus xs plus integration 0 to xs vs dash. Vs dash means the settling velocity of that particle considered. Vs is the settling velocity and settling velocity required. Dx, that is we have to sum all the particles so that we can get the overall percent removal. So these are the main things regarding the efficiency of the sedimentation tank. This concept is more important in case of sedimentation tank analysis. Now let's move on to sixth question. 8 mg of Copperas is consumed with lime at a coagulation basin per liter water. Determine the quantity of quick lime required to treat 10 million liters of water. So this question is based on the coagulation part of sedimentation. So they have used the Copperas as the coagulant. Here we have 8 mg of Copperas is consumed with a lime at a coagulation basin per liter of water. So per liter of water, 8 mg of Copperas is consumed. Then how much quantity of quick lime will be required to treat 10 million liters of water? So here the option A is correct, 16.12 kilogram. Let's see the calculations and concept. So first we should be aware of the equations involved in this Copperas coagulation. So Copperas is nothing but ferrous sulfate, FeSO4, hydrated ferrous sulfate, we have to say, FeSO4 7H2O plus this hydroxide, calcium hydroxide, on reacting with Copperas gives ferrous hydroxide plus calcium sulfate and water is the byproduct. So calcium sulfate is the non-carbonate hardness. So this contributes to permanent hardness that needs to be removed further. So after coagulation we need to remove this permanent hardness, that is calcium sulfate, and this FeOH twice is the flock. This is the flock when Copperas is treated. The Copperas is used as a treatment coagulant, and the molecular weight of Copperas is 278 grams. This 278 gram of Copperas need 56 gram of quicklime. So quicklime is nothing but calcium oxide. So calcium oxide on reacting with water gives the calcium hydroxide. So that calcium hydroxide will react with Copperas to give calcium sulfate as the non-carbonate hardness, that is permanent hardness, and this flock. This is the flock that is formed by this coagulant, so that this flock will settle out. So that is why we are using Copperas as the coagulant, and we have to calculate as per the molecular weight. So molecular weight of Copperas is 278, and 278 milligram of Copperas need 56 milligram of quicklime. How 56? Because quicklime is CaO, that is Ca has molecular weight of 40 plus oxygen 16. So 56 milligram of quicklime. If 1 milligram of Copperas need 56 by 278 of quicklime, then 8 milligram will require 56 by 278 into 8. We have 10 million liters, so into 10 million liters will give 16.12 kg as the answer. So this is a simple calculation, but we need to be take care of molecular weight of Copperas and also the molecular weight of quicklime. So molecular weight of Copperas is 278. So that 278 gram of Copperas will require 56 milligram of quicklime. So in this statement is more important so that we can calculate easily. Similarly, we shall see about the alum. So this question is based on the copper as coagulant, and we may also get questions from alum as the coagulant. So when alum is used as coagulant, how will the reaction goes? So aluminum sulfate, Al2SO4 thrice, 18H2O plus 3 in calcium bicarbonate gives calcium sulfate, aluminum hydroxide and carbon dioxide and water as byproducts. So here also calcium sulfate, that is permanent hardness, will be coming out as the product, and aluminum hydroxide is the flock that will be settling out. Now we shall see the same as we have seen in the Copperas. The molecular weight of alum will be 666 gram, and this 666 gram react with 300 gram of alkalinity as CaCO3. Why CaCO3 we are taking? Because CaCO3 on reacting with water gives calcium bicarbonate. So that is why we are considering calcium carbonate as the alkalinity base value. So here in the previous thing we used the quicklime, right? So similarly we are using here as the calcium carbonate. So 666 milligram of alum reacts with 300 milligram of calcium carbonate alkalinity. So that means 300 by 666 as the alkalinity of calcium carbonate when 1 milligram of alum reacts. And this is the basic equation we have to be aware of. When 1 milligram per liter of alum on reacting with 0.45 milligram per liter of alkalinity as CaCO3, not calcium bicarbonate. We have to be careful what is the alkalinity we are using. The alkalinity as CaCO3, calcium carbonate only. So 1 plus 0.45 milligram per liter of alkalinity gives 0.613 milligram per liter of non-carbonate hardness. That is nothing but calcium sulfide in this case, and 0.23 milligram per liter of flock. Here flock is nothing but aluminum hydroxide, and 0.396 milligram per liter of carbon dioxide. That is nothing but here we have. So if we remember these values, we can easily find the answer for questions when we are asking what is the amount of flock we will get when alum is reacted with this much of alkalinity, and this much of flock will be formed. So this is the basic and important thing we have to remember. So 1 milligram of alum on reacting with 0.45 milligram per liter of alkalinity as calcium carbonate will give 0.613 milligram per liter of calcium sulfate, that is non-carbonate hardness, or we can say permanent hardness, and 0.23 milligram per liter of flock, that is nothing but aluminum hydroxide, 0.396 milligram per liter of carbon dioxide. So carbon dioxide imparts acidity. And the doses of quicklime required when we are moving for alkaline deficiency is 0.56 into alkaline deficiency. When there is a deficiency in alkalinity, then we have to provide quicklime, that is CaO. So how much will be given? That is nothing but 0.56 into alkaline deficiency. This is how, these are the values we have to remember in case of Copperas and alum. Now we shall move on to the next question. A flask mixture of 2 meter cube with a velocity gradient of mixing mechanism equal to 600 per second. The fluid viscosity is given as 10 power minus 3 Newton second per meter square, which is continuously operated. What is the power input per unit volume? The question should be read carefully. What is the power input per unit volume? This is an important question regarding the flask mixture. In the flask mixture, we have these terms: velocity gradient, power, volume, viscosity. So here the correct option is option B, 360 watts. Let's see the formula. The temporal mean velocity gradient, that is given by capital Z is equal to root of P by mu into V, or we can simply say P is equal to Z square nu V. So P is the power that we have to find in this case. G is the velocity gradient that is given as 600 per second, and nu is the dynamic viscosity. We should be careful about the viscosity value, whether it is dynamic or kinematic. Kinematic viscosity will be applied for Stokes law, but here we are using the dynamic viscosity that is given by Newton second per meter square. Here we have 10 power minus 3, and V, capital V, is the volume. So volume of flash mixture is given as 2 meter cube. But the question is, what is the power input per unit volume? So per unit volume, what is the power? So G square into mu only will be the answer. What is G square? 600 square into mu, that is 10 power minus 3. So G square 600 square into 10 power minus 3 gives 360 watts. So we should be careful in the question. Power input per unit volume is asked. Now let's see more about this temporal mean velocity gradient. Generally we have G value as 2275 per second in general case, and G into TD, that is product of this temporal mean velocity gradient and detention time, shall be around 12,000 to 27,000. These are some general values. This temporal mean velocity gradient is a measure of relative velocity of two particles. If there are two particles, say this has two particles, and the distance between them as x, the measure of relative velocity of two particles of fluid and distance between them. So velocity between two particles as meter per second and distance between them as per meter. So that is why we are getting the velocity gradient in per second. So this is nothing but measure of relative velocity of two particles of fluid and the distance between them. And we have this formula also, P is equal to half into CD, that is coefficient of drag, and rho W is the density of water, and AP is the peripheral area, and VR is the relative velocity between those two particles. So by using this equation also we can find the power, or we can say temporal mean velocity gradient. So we have learned three formulas here, B is equal to G square nu V, and these two things. These two are similar. We can either follow this or this formula regarding the power and temporal mean velocity gradient. Now let's move on to 8th question. A filter bed is composed of 800 mm of unit size spherical sand of 0.5 mm diameter with a porosity of 45%. Calculate the head loss when the clean bed is operated at a rate of 145 meter per day. Kinematic viscosity of water is given. So here we have to find the head loss. We have to follow the kinetics of fluid or kinetics of sedimentation. So that concept has to be followed here so that we can find the head loss. Here the answer is option A, 0.28 meter. Now let's see the formula. So here we are using Karman-Kuznets equation of finding the head loss, that is HF is equal to Fz V square by ZD5 into 1 minus N by N cube. So here N we know, that is the porosity value is 45%. Here we have to substitute in decimal. So 1 minus 0.4 by 0.45 cube, and we have F. F is given by 150 into 1 minus N divided by RE plus 1.75, and RE is the Reynolds number that is given by here, Vd by gamma into phi. Phi is the shape factor. Shape factor will be applicable in case of irregular size particles. Here they have clearly mentioned as spherical sand. For spherical particles, shape factor will be 1. So Vd by nu only will be the value for Reynolds number. So that Reynolds number will be substituted here and porosity value, so that we can get the F value. And Z is the depth. But here they have clearly mentioned as head loss when the clean bed is operated at a rate of 145 meter per day. So here they have mentioned 800 mm of unit size. So 800 mm is the Z value, and we know 145 meter per day, but we have to substitute in correct units so that the equation is dimensionally homogeneous. So if we substitute the value, we will get the answer for HF as 0.28 meter. And this is the important thing regarding kinetics of fluid sedimentation or particle analysis. Now let's move on to the next question. Design 6 slow sand filters for a population of 60,000. The per capita demand is given as 200 liters per capita per day. Out of 6 slow sand filter units, 1 unit is standby. The rate of filtration is given as 150 liter per hour per meter square. The L is to B ratio is given as 2:1. So designing means we have to find the dimensions of the filter unit. So we have to find the length and breadth. They have given the length and breadth ratio as 2:1. Accordingly, we have to calculate the length and breadth values after finding the area of each unit. So this is based on the filtration, slow sand filter and rapid sand filter. We have two things. Here the answer is option D, 50 meter cross 25 meters, the dimension of the 1 unit of slow sand filter. Now we shall see the important things regarding slow sand filter. So design discharge, we have to consider the design discharge as 1.8 times the average discharge, that is MDD value we have to take 1.8 times the average discharge. So we know the average discharge value from the population and per capita demand. So upon finding the average discharge, we can find the design discharge. So after getting the design discharge, we know what is the rate of filtration. So dividing this both the things, we will get the meter square, that is area of one filter unit value. And if we find the area of one filter unit value, we can get the dimensions using the number of slow sand filters that we require. That is 5 plus 1. 5 filter will be in operation and 1 unit will be in standby. So this is a simple calculation, but we should be aware the design discharge value that to be taken is 1.8 times the average discharge. That is nothing but the MDD value. That MDD, MSD, these discharge design values are dealt in the water this video, water quality and basic treatment methods. Please watch this suggested video so that we can be aware of what is MDD, MSD value. And we shall see more about other points regarding slow sand filters. So D10 value is nothing but the effective size of the sand particles in slow sand filter, that is nothing but 0.15 mm to 0.35 mm, and the coefficient, that is uniformity coefficient, will be ranging from 1.8 to 2.7, and the depth of sand will be 90 to 120 centimeter or nearly 1 meter. The design period of a slow sand filter is 10 years. The cleaning part, this is most important thing, how the source sand filter will be cleaned. It is done by scraping of 1.5 to 3 centimeter of sand layers and occur a duration about 1 to 3 months. For every 2-3 months, scrapping of 1.5 to 3 centimeter of sand layers will be done. This is the cleaning of source sand filters. In general, the efficiency of these slow sand filters will be around 97 to 98%. If there is a pre-chlorination of that water, then the efficiency may move up to 99.9% efficiency. That is, all the impurities will be removed. The rate of filtration is around 100 to 200 liter per hour per meter square. This value is also an important thing. Rate of filtration is around 100 to 200 liters per hour per meter square. And the turbidity of the raw water should be less than 50 ppm. Then only we can use slow sand filters, or else we should move for pressure filters or rapid sand filters. The turbidity should be less than 50 ppm, because we are using the effective size and uniformity coefficient as much as low. That is, effective size of the sand particle is 0.15 to 0.35 mm, which is very less. So that is why we have to make sure that turbidity should be less than 50 ppm. Now let's see more points regarding rapid sand filter. So in case of rapid sand filter, the design discharge shall be 2 times the average discharge. Here we are not using 1.8 times. Here 2 times the average discharge. And similarly we are using the D10, that is the effective size of sand particle as 0.35 to 0.55 mm, which is higher than that of slow sand filter. And the uniformity coefficient is lower than that of slow sand filter, that is 1.2 to 1.7. This value is to be remembered. There may be asking in match the following. The depth of sand will be around 45 to 75 centimeter, which is somewhat lesser when compared to slow sand filter of 1 meter. The number of units required will be empirically found using this relation. N is equal to 1.22 root q. This is also an important thing. N is equal to 1.22 root q, where q in meter cube per second as usual. And here the cleaning will be done by backwashing. In case of slow sand filter, the cleaning will be done by scraping of 3 centimeter layer of sand. But here the backwashing will be done by using around 2 to 4% of total water filter. And this backwashing will be done at an interval of 24 hours to 28 hours at a period of 30 minutes or 15 minutes, like that, depending on the conditions. And the efficiency will be around 97 to 98%. No, it is not correct. It is, this efficiency is meant for slow sand filtration only. The efficiency is lesser when compared to slow sand filter, and the rate of filtration is 3000 to 6000 liter per hour per meter square, which is very higher when compared to slow sand filter. Now let's move on to the next one. Which relations are correct between the rate of backwashing V0, rate of filtering V, and the porosity of expanded bed N suffix E? So which of the following relations are correct regarding these three things: rate of backwashing, rate of filter, and the porosity of expanded bed? When there is filtration in rapid sand filter, the bed may be expanded, so that is why porosity may also change, which is given by N suffix E. So here we have options A and C as the correct one. Both are correct. One is V suffix naught, that is rate of backwashing is equal to V into Ne power 4.5, or we can use this relation. N is equal to V naught by V into V power 0.22. So these two relations are correct in case of rapid sand filter of expanded bed condition. This is also coming under the kinetics of filtration. Similarly, we have seen in the Karman-Kozeny equation. And the backwashing thing. During backwashing, the flow condition will be a transition. There will be no laminar condition or turbulent flow. The between which, that is nothing but the transition flow condition will be prevailing. So that is why we have to use the Hazen's equation when we are supposed to find the settling velocity at the backwashing period. We have to use the Hazen's equation, nor Stokes law, neither Stokes law nor Newton's law. So we have to use the Hazen's equation only during backwashing. And the head loss due to backwash is given by HF is equal to L into 1 minus N into S minus 1. And in case of expanded beds, expanded length we have to use, and we have to use the expanded porosity, that is N suffix E. And these are the things regarding the rapid sand filter. And the operational troubles in rapid sand filter are as follows: like formation of mud balls will be there, cracking of filters, air bending phenomenon. So these three things are the operational troubles in rapid sand filter, but these three things won't happen in case of slow sand filter. And we have crossed the 10 questions. Now we shall see 3 more questions as bonus. So first one, residual ozone is measured by. Which test will be used to measure the residual ozone? So these are some of the disinfection techniques. After sedimentation, chlorination, after sedimentation, coagulation, filtration, we have disinfection as the treatment part. And in case of disinfection, we use chlorination, ozone, KMNO4, like that. So we shall see one by one. Here, the residual ozone. Residual ozone, when treatment with ozone, which is measured by orthotoluidine test. These are the minor methods of disinfection: treatment with ozone, treatment with fluorine and bromide, silver, KMNO4, potassium permanganate, or with excess lime. So when we use these things, then there will be some amount of disinfection, and these will be coming under minor method. But the major method is the chlorination. And the residual chlorine is tested by these 4 tests: orthotoluidine, starch iodide, chlorotest, and DPD test. Now let's move on to the next method. Identify the freely available chlorine. This is based on the chlorination part. So during chlorination, many reaction will happen. So in this reaction, after forming the formations of this reaction of chlorination, the freely available chlorine are what? What are the freely available chlorines that will react to disinfect? That is acting as a disinfectant. So here we have H4Cl and OCl minus. These are hypochlorous products. Let's see the important equations that is followed in chlorination. So when chlorine is reacting with water, will form HCl and HOCl, hydrochloric acid and hypochlorous acid. So H4Cl, this reaction will happen only when the pH is greater than 5. And when pH is greater than 8, then this hypochlorous acid, that is H4Cl, will disintegrate into H plus, that is hydrogen ion, and OCl minus, that is chloride ion, hypochlorite ion. And this disintegrated particle will again react to form HOCl when the pH is less than 7. When the pH is greater than 8, the HOCl will disintegrate into hydrogen and OCl minus, and the same hydrogen ion and OCl minus ion will form a product, will act together to form HOCl as the product when the pH is less than 7. So we have to be careful about the pH values. So when pH is greater than 5, then chlorine will react with water to form HOCl. When pH is greater than 8, then HOCl will disintegrate into H plus and OCl minus, and H plus and OCl minus ion will react together to form HOCl when pH is less than 7. So these two reactions are important for the formation of these two disinfectants, that is nothing but the freely available chlorine. And when the water is containing ammonia, that is NH3, then ammonia will react with hypochlorite ions, that is HOCl, to form chloramines. First, ammonia reacting with HOCl to form NH2Cl. So this will be happening when pH is greater than 7.5, and when pH is less than that is 5 to 6.5, then again that chloramine will react with HOCl to form dichloramine. And when again the pH is less, that is less than 5, then the chloramine, that is dichloramine, will be reacting with HOCl to form trichloramine. So these are the chloramines which will be acting as a disinfectant also. But the HOCl product is the most powerful disinfectant, and which is 80 to 100 times more powerful than OCl minus. And we have various forms of chlorine, so that we can fetch these chlorination things. One is bleaching powder, we can chlorinate via bleaching powder, or we can use free chlorine, and we can use chloramines, and we can use chlorine dioxide. And chlorine dioxide is also a more powerful thing, which is around 2.5 times more than these hypochlorite ions, like that. So this is also more powerful disinfectant. Now let's move on to the next one. So this is the last bonus question. Chlorine gas used to do disinfection combines to water to form HOCl. This we have already seen in the previous thing. HOCl ionizes to hypochlorites and H plus ion. This equation is also we have already seen in the previous thing. And rate constant is given as 2.7 into 10 power minus 8 at 20 degrees Celsius. And 90% of HOCl is free residual chlorine that is available at a pH of which pH 90% of HOCl will be freely available as a residue. So that we have to calculate. So the pH value is asked. Here we have to follow one simple equation, reaction product equation, but use the rate constant value that is given 2.7 into 10 power minus 8. Here the correct option is option A, 6.61. This is the simple formula we have to use to find the pH. So percentage HOCl is equal to 1 by 1 plus K by H plus into 100. So we know percentage HOCl, that is 90%, equal to 1 by 1 plus K that is 2.7 into 10 power minus 8 divided by hydrogen concentration. So by using this equation we will get the answer for hydrogen concentration. So after getting the hydrogen concentration, we can find the pH value. So pH is nothing but minus log of hydrogen concentration. So simply finding the hydrogen concentration value, we can find the value of pH. Here we have got the answer as 6.61. So this is the basic graph, the percent HOCl and percent OCl minus versus pH. So this is will be nothing but a S curve. So we can observe what is the value of percent HOCl at this pH value. So when pH is very less, then OCl, then HOCl will be high. Then when pH is very low, then percent OCl will be high. And let it be clear, when pH is very less, we have higher percentage of HOCl, and when pH is very higher, that is higher end, then the dominating chloride ion is OCl minus. So when pH is very lesser, then dominating hypochlorite thing is HOCl, and when pH is very large, then dominating thing is OCl minus. Now let's move on to the breakpoint chlorination. Let's see this graph. So total chlorine residual in y-axis and the chlorine added in x-axis. So at initially there will be no reaction because the chlorine will be destroyed by reducing agents. So this part, initial part, there will be no reaction for chlorination because chlorination or the chlorine will be destroyed by reducing agents. So after some time only chlorine acts to form monochloramine, dichloramine. So there will be a combined chlorine residual. So formation of monochloramine and organochloramine, that is mono, di, these things will be happening, combined chlorine residual. So after that monochloramine is destroyed forming dichloramine, and after that there will be a breakpoint. So after this breakpoint, whatever the chlorine that we add will be a residue or will be overdosage, we can say. So free chlorine residual will be happening. So breakpoint chlorination means the chlorine we are adding after the breakpoint. So that is the breakpoint. All ammonia is oxidized into nitrogen gas, nitrate or nitrogen trichloride at the breakpoint. And after the fourth stage, we have freely available chlorine residue. So this is the breakpoint chlorination mechanism. And the free residue along with trichloramine. So we have these two things and combined chlorine residual. We should be aware of this chart, and at the first stage, at the initial time, the chlorine will be destroyed by reducing agents. Now let's see the other minor things. Activated carbon will be used to reduce or remove color, taste, odor and phenol type impurity. The dosage will be around 5 to 20 mg per liter. And copper sulfate will be added to remove color, taste and odor, and the dosage will be around 0.5 to 0.75 mg per liter. And fluoridization, when we want to add the fluoride, then we can use these chemicals, NaF, these chemical compounds, sodium, silicate, like that, H2, Si, F6. And when there is a excess fluorine, then we have to remove that. So that is called as defluoridation by using Nalgonda technique or Prashanti technology. That is nothing but activated alumina. So these are the things we are using for fluoridation, defluoridation, and these are the minor things regarding disinfection and the treatment of water. Now we are at the end of this video. We have learnt about the almost all aspects of treatment of water, starting from pre-treatment, screening, sedimentation, coagulation, flocculation, and what are the types of settling, phenomena, and we have also studied about the disinfection techniques. Hope you enjoyed this video. Please like, comment and share with your friends, and also watch the suggested videos. Thank you for watching.